All right. So thank you all for coming. It's a pleasure to be up here in front of you today to be able to talk about building hybrid Rust and C# apps without sacrificing safety or too much sanity. There's a little sanity loss, but I promise it's not too much. First, a little bit about me. My name is Ash. You can find me around on GitHub and Twitter and various other channels under the CoderOz handle. I'm part of the Rust Libs team and an engineer at Datalust, where we work on a diagnostics platform called Seek. So we're going to be looking at running Rust and C# together in a single application. I'm not going to try and convince you today that this is actually something that you're going to want to do, because while C# and Rust are independently memory-safe languages, the only way we can stitch them together is by pretending that they're C. And so that means throwing out all the safety that we're used to working within them and having to rebuild that ourselves. And doing that requires a fairly deep understanding of both the .NET runtime and the Rust language. What I am going to try and do is use the process of having to explicitly work with language and runtime features that are normally at work for us implicitly to offer a fresh perspective on these languages. So if you've mostly been working in safe C# for a long time, then there are aspects of the C# language and the .NET runtime that you might not have actually come across before, even though those will be at work somewhere in the stack that you're working with. And so having a look at those explicitly may give us a fresh appreciation for this workhorse language that we use every day and the kinds of things that somebody has had to do in order to make the code that we write safe. Similarly for Rust, if you've had a look at the language in the past, or you've tried to pick it up and couldn't quite get why the language is designed the way it is, what it's actually trying to achieve, why various features work the way that they do, then seeing them at work for us today in the real world context of rebuilding safety in a hybrid app may help us build additional context and a deeper understanding of this language so that we can feel more productive when we use it. So I'm not going to be assuming too much familiarity of Rust coming into this, but we're going to be looking at weird and unsafe code for the most part. So we're not going to spend a lot of time fussing on syntax. We're going to be focusing on concepts, how those broader concepts map to language features, and how those language features help us build safety. So this is going to be less a gentle introduction to Rust and more a fire hose of Rust right to the face. But we should be able to follow along just fine. Okay, so let's start with a little bit of background. So I mentioned I work on a diagnostics platform called Seek. This is Seek. It's really a database. You send it diagnostic data in the form of buckets of structured logs. Seek will then organize those on disk for you and allow you to query them back using its SQL-like query language. So Seek is a database that is specialized to a very particular workload, and that's ordered range queries over semi-structured time series data. That's really what Seek is. At the start of 2018, Seek was a Windows product, built on the full .NET framework in C# with some fairly deep ties to the Windows platform. Over the course of that year, we broke that dependency on Windows, and we shipped a new version of the Seek product with support for Linux and Windows based on .NET Core. So Seek's dependency on Windows went right to the heart of the database, and the heart of a database is its storage engine. So Seek would be organizing its data on disk using Essent. Essent is this database suite that's baked into Windows. It's used by various Windows features. And so we would have our high-level event store organizing data into 7-day blocks. Each block would be an Essent database. So we had to break that dependency. But it wasn't just a matter of breaking our dependency on Essent in order to move to cross-platform. One of the issues with Essent is that as like a disk-backed B tree, it wasn't really ideal for Seek's workload of semi-structured data. So rather than just replacing Essent with some equivalent cross-platform solution and accepting exactly the same trade-offs that we already had, we thought it would be better to build our own storage engine, because why not, you know? Can't be that hard. So that's what we did. We built a storage engine, and we built it in Rust. So now we have a C# database and a Rust storage engine. And we can see now that we get visibility all the way from the high-level C# event store right through to the individual Rust components in the storage engine, and then down to actual files on disk. So what we're looking at here is a hybrid app. But what is a hybrid app in the general sense? We can think of a hybrid app as many languages, many runtimes, and many paradigms all bundled up together in a single F5 experience. So to give you an idea of what I mean, if you're mostly working on line of business applications in .NET, then you might be familiar with this kind of stack. You have something like a C# server, a JavaScript or a TypeScript client, and the two are connected via a HTTP API. Oftentimes, the JavaScript client is the only consumer of your C# server, so they're logically one system that are coupled via an API, and they present a single experience to the end user. But they're separate runtimes. The kind of hybrid app we're going to be talking about today is having C# code and Rust code coexisting within the same actual process. And rather than communicating via a HTTP API, they communicate via a shared application binary interface that allows the .NET runtime to call Rust functions. So why would we actually want to do this? It kind of sounds like a lot of work already, so why would we take our existing C# database and then throw Rust into it? Why didn't we build our storage engine in C#? Or alternatively, why didn't we go the big bang, rewrite it in Rust path, throw out all of our existing code, and try and build a new Seek from scratch in Rust? The answer for us comes down to language trade-offs. Fundamentally, all languages are designed with trade-offs in mind. There are no free lunches, so there is no universally perfect language, as much as we might like to think there is. And so Seek, as a fairly large product, has different requirements for different components. As our storage engine sets the low watermark for our performance characteristics, and it sets the high watermark for our safety. So what we need is for the runtime performance impact of our storage engine to be as low as possible, so we have as much room to move as we can for high level features on top. And we can't build a database on top of our storage engine that's any safer than the storage engine itself is. Because while reliability doesn't guarantee safety, if we have an unsafe or unreliable storage engine, then it's going to be very hard to build a safe database on top of it. And Rust is really geared to that kind of code, that safety and performance critical code. But not all of Seek is like that. We also have higher level features. We have domain entities, we have migrations, we have components that need to interact and deal with versioning over time. We have a web API, and all of that stuff is bread and butter for C#, because it's a very concise and productive language with great dev time tooling, and it has a lot of mature libraries. Like it or not though, it's not just a case of being able to pick and choose the languages that you want from the language tree, take the things that you like out of those, and ignore the constraints. Because there are no free lunches, we can't build a hybrid app without accepting new trade-offs. There's real complexity in stitching two language runtimes together. But what's important is how this complexity manifests itself throughout our system. So what we end up with is localized, concentrated complexity in the stitching layer that doesn't need to permeate through the rest of the code bases. So what we end up with in Seek is this very large, safe, idiomatic C# code base, a large, safe, idiomatic Rust code base, and then this thin slice of insanity in the middle. And it's that thin slice of insanity that we're going to be looking at today. So why Rust? I've kind of implied up to this point that Rust has something to offer us when building a storage engine that we felt made it more appropriate than C#. So I mentioned that our storage engine sets the low watermark for our performance characteristics. In order to build high performance C# code, we need to limit GC work. Limiting GC work means relying on value types. As a bit of a thought exercise, let's pretend that C# only had value types. So exactly C# but no classes. If you try to build a system in this language, what kinds of limitations would you expect to hit? If you've tried to build code based on structs, you can probably think of a few already. The answer, though, is fewer limitations in C# today than in the C# of yesterday, say between C# 5 and C# 8, with the introduction of ref structs, disposable ref structs, ref read-only fields, ref locals, ref returns. All of these things make value types more capable and make working with them more ergonomic. If you keep following that path along into the future, you might end up with a language that looks like Rust. Will C# 15 have a borrow checker? Who knows? So we can really think of Rust as .NET value types with special superpowers, because Rust is fundamentally data types, fundamentally value types. It makes them nice to work with. So anything that you wish you could do with value types in C# but felt like you couldn't, you probably can do in Rust. What that means is that when we're writing Rust, we get the benefits of writing with value types. we get a stable runtime with low overhead. We have zero cost abstractions because things are stack-based. When you're writing performance-sensitive Rust code, you can use closures. You can use iterators, which are Rust's version of LINQ. So we don't have to work in a subset of the language and compound the inherent complexity of building a storage engine with the complexity of knowing what features of the language we're allowed to use. Rust also has a strong safety culture, so there's a lot of knowledge sharing about what kinds of unsafe code are okay to write and what kind aren't and why. And that's important when you're writing this kind of code as well. All right, so let's actually take a look at this Rust language. And we're going to do that with some C# equivalents. The goal isn't really to do a Rust versus C# kind of thing. That's not very useful. The idea is, assuming that you're more familiar with C#, we can build some context around how Rust approaches the same kinds of problems. All right, so let's have a look at some structs. So in C#, we declare a value type as a struct. It can have fields. In Rust, we declare a value type as a struct, and it can have fields. So far, they're fairly similar, but there is one difference already, and that's that little derive annotation. In Rust, that hash derive is an attribute, and like attributes in .NET, they allow us to annotate our items with additional semantics. In this case, that derive makes the semantics of our Rust struct equivalent to the .NET struct. So in .NET, all value types have an initial default valid value that you can initialize them to, even if that default doesn't make semantic sense for that struct. In Rust, we have to opt into that by deriving default. In .NET, we say that value types have copy semantics. When you pass a value type by value into a method, a copy of that value is made, and that's what you work with in the method. When the method runs out and you go out of scope, then any changes you made to that struct will be lost. In Rust, we say that structs have move semantics by default. So when you pass a value type by value into a method, a copy is still made, but the original is invalidated. And the one true version of that instance is passed into that method. When it goes out of scope, then Rust will destroy it. We can opt into copy semantics in Rust, though, by deriving clone and copy. So we see immediately some differences between how value types behave by default in Rust and C#. But we don't just declare values and pass them around by value, we share them. So ignoring object references, which are overwhelmingly the most common way that we share data in C#, what does .NET give us to share value types? It gives us managed pointers, which are a feature that you might not have actually looked at directly because C# doesn't expose them directly. That's that little T and in the left-hand side there. That is a managed pointer. It is a stack-based GC-aware reference to some data that may be on the stack, on the managed heap, or it may be unmanaged altogether. So while C# doesn't expose them directly, it has a bunch of features that use them. Ref parameters are like a shared mutable reference. We have a recent addition in T, which is a shared immutable reference. Ref locals, ref returns, and ref fields, those are all based on managed pointers. They allow us to share data in a memory-safe way. Rust has its own safe way of sharing value types, and those are references. So we talked about the own T move semantics. Rust has shared immutable references, and it has exclusive mutable references. And so the rules in Rust are you may have a bunch of shared immutable references, or you may have one single exclusive mutable one, and you can only mutate data through a mutable reference. So we also see that Rust references don't just track mutability, they also track lifetimes. If you're familiar with F#, you might recognize that tick A, which is a lifetime, as a generic type parameter. It's not really a coincidence because lifetimes in Rust are types. They're types that tell us the points in our program for which that reference is valid and can be used. We track that lifetime explicitly through the type of the reference. What does that actually give us though? So as an example, to see what explicit lifetime tracking buys us, let's have a look at value types that borrow data. In C#, if we want a value type that contains a managed pointer internally, we declare it as a ref struct. We can then give it a span of bytes, which is borrowing from somewhere else. In Rust, an equivalent struct looks like the one on the right. We have a borrowed type. It takes a lifetime, which we've called tickref, as a generic type parameter, and we can then use that lifetime for references in its fields. So that and U8 there is a slice. It's pretty much the same thing as a span of bytes. And so in Rust, we say that a struct inherits the lifetime of its fields. So because borrowed has a lifetime tickref, the borrowed struct itself can't outlive that lifetime, otherwise it would be pointing to invalid data. So we say that borrowed lives for tickref. Managed pointers in .NET manage their lifetime heuristically by being bound to the stack. You can't box a managed pointer because it may point to stack data and then you would invalidate it. Because in .NET, when we box a value, we talk about promoting it to the managed heap. We change the semantics of its lifetime. When we box a value, the GC takes ownership of it and it won't reclaim that value until it's no longer reachable. So we say it has an arbitrarily long lifetime, whereas on the stack it has an arbitrarily short one. So it's not valid for us to box borrowed structs in C#. As a consequence of that, we can't use borrowed value types as generic type parameters, because in .NET we assume that it's valid to box a generic. Rust doesn't have that same restriction. It's totally okay for you to box borrowed data in Rust. Because Rust's heap doesn't add semantics, it's just an allocation space. Our allocation there won't outlive the borrow of some slice that we pass in. It's a bit of a pointless box, but you can still do it. We also have no problem passing borrowed data in Rust as generic type parameters because the lifetime becomes part of the type. Rather than assuming, say in .NET, where it's valid for us to extend the lifetime of a generic type, in Rust we assume that that t value is only valid for the block or the scope of takes generic. So we have restrictive default type constraints rather than permissive ones. So that's a whole lot of words, but what does it really mean? So to give you an example of what these things that we've just talked about get us when writing real code, let's have a look at some bad code that I wrote. So this is a method in C#. It has a bug in it. It's not even a very long method and I still managed to screw it up. But in my defense, I didn't actually write it broken to begin with. I refactored it broken, which, I don't know, I guess that makes it a little better. If you're looking for the bug, just follow the sunglasses. The problem there is we rent a buffer from our memory pool. We need to dispose it to return it, so we make a using statement in there. We then logically move ownership of that rented buffer into our data that we return, but before we return our data, we're going to return the buffer to the pool. If we desugar that code, we can see it a bit more clearly. We create our data that we're going to return, dispose the buffer, and then return the result. Somebody else is going to rent that buffer. We're both going to be slapping bytes into it at the same time, and we have a data race. And that's a bad time. The problem here is that C# is relying on us to be good programmers, which I am at least not, so I end up writing bugs like this and have a bad time. If I translate this code directly into Rust, it actually looks very similar because my C# is kind of rusty. It looks pretty much the same, but there's one difference. And the difference is that we don't have the same bug. Because Rust tracks ownership explicitly, it knows that when we pass ownership of our rented buffer into the data that we return, it shouldn't return it to the pool until data goes out of scope. And that's move semantics at work for us. The compiler generates the right code rather than relying on us to do it. What if we try and desugar our Rust the same way as the C# though? In this case, we get a compile error. And the problem here is move semantics at work again for us. Rust knows that we moved our buffer into data. It's not valid for us to try and drop it. So drop is kind of similar to dispose in Rust. So we get a compile error instead of a data race. Up till now though, it might feel like I've been picking on C# a bit. That's not what I mean to do. There's a reason that Seek is predominantly written in C#, and that's because it gives us a lot too. And one thing that we can't overstate is the maturity of its ecosystem. So we get ASP.NET Core, which is this vast, capable, mature web framework that's suitable not only for our high throughput ingestion needs, but also our more standard web API calls that power the UI. And there just isn't that same level of maturity in Rust web frameworks yet, because ASP.NET's been going for like 15 odd years or something. We also get mature projects in the ecosystem like Serialog for logging and AutoFact for IOC. I think AutoFact deserves its own slide because it captures a pattern that allows us to scale C# code bases really effectively. So what we're looking at here is AutoFact at work, not just mapping abstractions to implementations, which is the least interesting thing that an IOC container will do for you, but it describes relationships between the components in our system and how those come together. So in this case, we collect all of our server tasks at runtime, along with some metadata about how to schedule them, except for our metrics task, which we deal with explicitly. And without reflection, you just kind of can't write the same code in Rust. You have to know everything up front. Something else that we get from C# is the compile time and the dev time tooling. So as an example, our C# seek codebase is about twice the size of our Rust codebase. Compiling C#, compiling our seek project in a fresh debug build takes about 3 seconds. For our Rust codebase, it takes about 2 minutes. And the reason they're different is that in C# we compile ahead of time to an intermediate language and then JIT it at runtime into machine code, whereas in Rust, we compile ahead of time using an optimizing compiler LLVM straight into machine code. So this is really an apples to oranges comparison, but that's also kind of the point, because sometimes you want apples and sometimes you want oranges. All right, so we've had a look at what a hybrid app is, why we might want to build one, why we decided to build one, and what we think Rust and C# each bring to the table. So now let's have a little look at how we go about stitching them together in a single application. So to do that, what I've done is I've hoisted our FFI infrastructure out of Seek. I've thrown it up on GitHub with a sample C# API on one side and a sample Rust database based on a project called Sled on the other side, which you should also check out. And I've put that up so that we can have a look at how we go about doing this. It's permissively licensed, so you can pilfer it to your heart's content. This is what it looks like. So it is a fairly extensive example. It covers a whole lot of things that we can't cover directly today, like how to integrate cargo with MS Build, how to debug .NET code using LLDB, all that kind of stuff. So I encourage you to check it out if you're interested in exploring this stuff further. So it includes a C# web API and a Rust database, and this user interface, which deserves no further discussion. This is not Seek. This is my amazing playing around with Angular. But what it allows us to do is create a document in our database, and we're going to have a quick tour of how our hybrid app works by creating a document. So we'll say, hello Oslo, and it's cold here even though it's summer. I don't know if anyone else has noticed, but I sure have. It's actually the same temperature in Australia at the moment, even though we're in the middle of winter, and you guys get like 18 hours of sunlight. It's insane. So when we set that, okay, so here we are in our sample app. We're on the C# web API at the moment. So what we've done is we've posted a JSON document to this endpoint. We're going to collect that up with its key, and we're going to write that to our database. So what we do is we read into an iMemory owner. This is a new API in C#. It represents some owned piece of memory that we're responsible for reclaiming. So we transfer ownership of the memory into our data struct. Now we need to begin a write transaction. So to do that, we call into Rust. So this bindings.dbWriteBegin here, this is a Rust function, and it's going to return a write transaction for us to use. So here we are, now we're in Rust. In order to begin our write transaction, we allocate a handle in Rust's heap. Allocating that handle means calling into our idiomatic Rust database, which in this case is fairly simple. We just create a clone of it. So once we've allocated our handle, we return OK. Now we have a write transaction, we can begin, we can actually set our document. So to do that, we copy the data key into a stack local. In this example database, our keys are a fixed 16-byte value. Because it's on the stack, it's okay for us to take a pointer to it. We get a fixed pointer to the value, which we can see has the content. And now we're going to call another Rust function. So back on the Rust side, we rematerialize our view of the data based on the inputs that we got from C#, and we set it in our database. That's not very interesting, so we'll just skip over that. We return OK. So now that we've set our document, we dispose our write transaction, and that means calling dispose because we had it in a using block. Calling back into Rust, we call complete. That flushes the bytes that we just wrote to disk. We then complete our action, and now we have a document saved in our database. So that's a quick view of this sample app that we're going to be looking at. And I cannot enter gestures. So there were a few pieces in there. We have a C# API, we have some C# bindings, we have some Rust bindings, and we have a Rust database. So the first thing that we're going to look at are the bindings, the C# and the Rust side. And these are the fundamental way that we stitch these two languages together. They're effectively C functions. What we do is we declare them and implement them in Rust, and we then import and call them in C#. What's important is that various parts, aspects of these functions line up. They need to have the same calling convention, so we know who's responsible for cleaning up the stack. They need to have the same name, so that in C# we can find them. That's what that little nomangle attribute does. It stops us from messing with the name of the function that we export. And they need to have the same arguments, and those arguments need to have the same ABI. That means they need to have the same representation in C# as they do in Rust. So what actually happens when we execute a Rust function in C#? We don't just call it directly. There's a feature of the .NET runtime called PInvoke that comes into play here. And what PInvoke does is when the runtime encounters an unmanaged call, it generates a whole lot of code around it to make sure that unmanaged code integrates into the .NET runtime correctly. So believe it or not, your C# code that you write that is executing in the .NET runtime has a specific ABI that it has to conform to, because the .NET runtime needs to be able to work with that managed code. In order to do GC reporting, .NET will walk all of your managed stack frames and try and find GC routes in specific locations so that it can report them to the garbage collector. We can't guarantee that unmanaged code is going to report its stack frames correctly. Similarly, threads that are running managed code need to cooperate in the runtime to decide when a GC should actually occur. Once again, unmanaged code isn't necessarily going to do that. So what we do is, before our unmanaged code, we tell the runtime that we're going to enter an unmanaged context. It knows to skip all of those unmanaged frames when it does a stack walk. It knows not to block on that thread if it needs to do a GC. And when we return, then the .NET runtime will check whether a GC is in progress and make sure that it waits appropriately for it. So the PInvoke is that little IL stub PInvoke there. We don't actually write that. That is generated for us by the .NET runtime. And that's also a place for special marshalling to occur for arguments that need to be converted into an ABI compatible representation. So below that PInvoke, we have our C# stack trace, and above that PInvoke, we have our Rust stack trace for the function that we actually called. So PInvoke introduces costs on executing unmanaged code. You're probably not going to be able to build a hybrid app with piecemeal functions written in Rust if you think it's going to make your code faster. The reason is that the cost of the PInvoke may well just dwarf the cost of the unmanaged function call, and then you've just wasted your time. In our case, pretty much every unmanaged function call means pulling data from disk or writing it to disk, so that's going to obviate the cost of pretty well anything that we can do on either end. So right now we have bindings. They're effectively C functions. We have no safety around them. In order to rebuild safety in these bindings, we use some special types on the Rust side, because Rust is really nice for modeling safety contracts. That's the place where we rebuild our safety. So there's a couple here that we're going to look at. There's this ref type, there's an out type, there's handle share thing, and a DB result. So let's have a look at DB result first. DB result is about error management. In .NET, our mechanism for error management are exceptions. Methods can throw exceptions, we can catch them, rethrow them, we have finally blocks where we can execute code regardless of exceptions. That's how we do it in .NET. In Rust, error management is done through result. We declare a method as fallible explicitly by making it return a result, which may be one variant, OK, in this case unit or void, or some error. We can't get at the OK result without exhaustively matching on the result that we get and handling the potential error case. The overwhelmingly most common thing that you're going to want to do if you get an error in Rust is simply punt it upstream for somebody else to deal with. And that's what that little question mark operator does. When we're in the body of a fallible method, we can call other fallible methods. We can use the question mark to early return with an error, and at that point we know if we're continuing, then it's OK, so we can use the OK variant. And that's how we do error management in Rust. So what we really want is to use the idiomatic error management strategy in either language. We want to be able to return errors with Rust using question mark, and we want those errors to throw as exceptions in C# that we might want to catch. Doing that demonstrates a problem with our FFI though, and that is that we're restricted in the kinds of data that we can send to and from the boundary. Rust's result is a special kind of enum that doesn't have a representation in .NET, even though I'm sure you'd all really like there to be one. So we can't just send a Rust result over the FFI boundary. We have to declare our own. And so that's what we do. That's what DB result is. That Reaper C there is an attribute that says lay this thing out the same way that C would, so that we have a common ABI that we can use on C#. So our DB result has a kind, which is a 32-bit value. It can be OK or an internal error or a couple of other variants depending on what's going on. It also has a 32-bit ID. So in total, our DB result is a 64-bit value that we return from our FFI. On its own, though, that DB result doesn't actually give us a lot of information. If we get an internal error, that doesn't really tell us why we got one or what we can actually do about it. So in order to send diagnostic information across the FFI boundary, we do the same thing that Windows does, which is when an error occurs, we set some more diagnostic information in a last result, a thread local buffer. If we get an error in C#, it could then read the contents of that buffer and format them into an exception message. So that's what this last result is all about. What that means is now in our binding function, we can use the question mark operator, which we hook into. So if we're returning a DB result and we question mark, we automatically format that error into our thread local buffer and return with DB result internal error. On the C# side, we have an equivalent implementation of DB result. It has a kind and an ID. It has a struct layout of sequential, so it's laid out the same way that the Rust one is. And when we encounter a DB result, we check it. If it's OK, we just return. Otherwise, we get the contents of that thread local buffer and we check the IDs match. That's why it has an ID on it, because if we don't check in between an error, then we won't. We might end up formatting the wrong error message into our exception, and things will just get even more confusing. So that's what DB result is all about. It's about error management. Now let's have a look at ref. So ref is about how we share data from C# across the boundary to Rust. So Rust doesn't understand .NET's managed pointers, which we talked about before, and C# doesn't understand Rust's references. So in order to share data across the boundary, we use unmanaged pointers. In .NET, we have this T* variant, which is typed, and we have the untyped int pointer variant. There are some subtleties with unmanaged pointers though, because as they are so named, they are unmanaged. Whereas with managed pointers, they integrate with the GC in two interesting ways. The first is that managed pointers participate in determining the liveness of the pointee. So when we're checking whether or not a value is reachable, if we can reach it through a managed pointer, we know that it is. Secondly, when the GC performs a collection, it may move objects around in order to prevent fragmentation. That means the actual address of a value can change basically between any two statements. When that does happen, we will update managed pointers automatically, so you don't even need to know. Unmanaged pointers don't participate in any of that. And if you end up running afoul of either of those things, then you create what's called a GC hole. So in order to get the unmanaged address of some managed data, we have to be in an unsafe context, and we use this fix statement. It means that within the body of that fix statement, we won't collect the value that we've got the address of, and we won't move it if a collection occurs. So that pointer is only valid for the scope of that fixed block. Once we have one, we can pass it through our FFI. Rust has its own version of unmanaged pointers. They're just raw pointers. We have the *const t version, and we have a *mute t version. Besides variance over t, where *const t is variant and *mute t is invariant, they're more or less the same thing. You can freely coerce a *const into a *mute. What they give us is documentation as type style thing, where you treat a *const as like a shared reference, so you shouldn't mutate it, and if you have a *mute, then you probably own it, or at least have an exclusive reference so you can mutate it. Raw pointers in Rust have their own weird interactions with the safe memory management system. In this case, we can convert a raw pointer into a safe reference, but there is a subtlety, and that is in that lifetime. So we call that lifetime tick unbounded because that's what it is. Typically in Rust, when you borrow data, you borrow it based on a borrow of something on the input. In this case, we don't have that. So that lifetime is kind of hallucinated. It comes out of nowhere. And what Rust will do if it encounters one of those is it will just use any lifetime that makes the code compile. So it's actually not a useful lifetime at all. We could accidentally extend that value and use it after it's valid, which would be a really bad time. So the ref type is here to fix that. It has a reaper of transparent, which in Rust means that it has the same ABI as its one-sized field. So in this case, when we receive a raw pointer, we simply interpret it as a ref and we get safety. There's no other changes to the way that we pass the type that are needed. We see that ref has a lifetime on it, tick fixed. We call that lifetime tick fixed because that represents the lifetime of the fixed block from which that raw pointer was acquired. And if we remember from before, we say that structs in Rust have a lifetime bound to the lifetimes of their fields, then we say that ref can't outlive that fixed block from C# for which the raw pointer is valid. Similarly, rather than returning a reference from our ref that has an unbounded lifetime, we bind it to a borrow of the ref. And if we remember, the ref itself is only valid for the fixed block, so the borrow of the data we get out of it can only be valid for the fixed block. And so that prevents us from being able to borrow data that would outlive the point from which that data is actually valid that we got from C#. So that's ref. Ref is about sharing readable data from .NET into Rust. Now let's have a look at out. So out is about write-only arguments or out parameters. In C# we have out parameters. We usually use them because we wish we had enums, but we don't, so we use out parameters. But they're fairly interesting in their own right. Because we're expected to initialize an out parameter as an optimization, they may be pointing to uninitialized memory to begin with, because we can't read it without initializing it. Rust doesn't actually have a concept of out explicitly, at least not yet, so we declare our own out pointer. It looks fairly similar to ref. It has that same tick fixed lifetime, which once again represents a fixed block in C#, but it's a little different. Because uninitialized memory in Rust is rather weird and tricky compared to uninitialized memory in .NET, which is actually fairly hard to get a hold of. So in Rust, there is a lot of undefined behavior to be found by creating references to uninitialized data. It's especially undefined behavior to dereference uninitialized data, but Rust may be doing that without you knowing it. So for instance, if we simply write a value through an exclusive reference into an uninitialized value, Rust will move out of what was already there, which is not valid because it was garbage. So for any arbitrary value, the only valid way to initialize it in Rust is by using this pointer write method. It's quite subtle, so we create this out type to encapsulate that so we don't accidentally dereference uninitialized memory and do something really weird. There's one exception though, that's fairly significant, and that's this read trait. So in Rust, we can think of read as like the read side of streams in .NET. They allow us to pass a mutable byte buffer that data will be read into, and we can then use that. We really want to be able to pass an uninitialized byte buffer into this though, because we don't want to have to initialize this enormous buffer full of zeros, only to immediately initialize it with some other values right away. So this kind of has to be defined behavior, even though there are some people in the Rust community who would really like it not to be. So what we say is that when our out parameter is pointing just to raw bytes, we have additional things that we can do with them that we're sure are going to be okay. We can get an exclusive reference to that uninitialized memory if we pinky promise that we're not going to read it. We can also initialize it with a slice of bytes. Because there's no drop semantics associated with those bytes, we're not going to create two copies of the same thing. So that's what out is all about. Ref and out are about short-lived references from C# data that we share in Rust. Now let's have a look at this handle shared. So handles are really the meat and potatoes of how we build safety in the FFI. We've looked at short-lived data so far. Handles are for long-lived data, data that is valid across multiple FFI calls. So we think of our handles as a pair. There's a C# component and a Rust component to them. The C# component manages ownership of some resource that was allocated in Rust's heap, and the Rust component manages access to that resource. So on the C# side, we take ownership of the Rust value. We make sure that it's reclaimed using the tools that are available to .NET, that is, using the garbage collector. We make sure that if that resource is reclaimed, it is only reclaimed once, but C# doesn't guarantee synchronization of access to that resource. So that's the responsibility of Rust. So the way that we declare our handles in C# to satisfy this contract is by using safe_handle. This is a thing that's been around in .NET since like .NET 2. It's been around for a long time. It's a class that wraps up a untyped handle, pointer to a handle. It gives us some point to implement to know whether or not the handle is valid, and it gives us some code to implement to actually release the handle, which will mean calling some Rust function to deallocate it. We can't deallocate Rust from C#. We have to call into Rust to do it. What safe_handle gives us is an implementation of dispose that synchronizes the calling of that release handle that we can call manually, and it gives us a finalizer. If you haven't worked with unmanaged data in .NET before, you might not have seen a finalizer. That's that little tilde safe_handle at the bottom there. Finalizer is really a way that we can plug code into the GC so that we can run our own code when a collection runs over our value. And in this case, the finalizer makes sure that we call release handle. So even if we don't manually dispose it, it will get cleaned up for us. Safe_handle inherits from this thing called critical finalizer object. In .NET, as a general rule, pretty much anything that inherits from critical something has some kind of runtime semantics associated with it. In this case, it makes sure that if we do reach finalization, then the finalizer of our handle runs after everything else, just in case there are other objects we collected that still need to access it. So there's a lot of subtlety around cleaning up unmanaged resources, and safe_handle takes care of those for us. There's actually another subtlety as well around the synchronization of reclamation, and that is safe_handle makes sure that we can't reclaim an unmanaged resource while there might be unmanaged code using it. And the way it does that is through reference counting. So internally, our safe_handle has a reference count. Because safe_handle is understood by the .NET runtime, in the PInvoke stub that we generated earlier, it will generate code around our unmanaged function to increment the ref count before our unmanaged call and then decrement it afterwards. So that if we're within DB read next here, we can't release the handle. It'll wait until we return. So as an example, here's what one of our handles looks like. It's fairly simple. We just say the handle's invalid if it's 0, and releasing it means calling a Rust function. Even if that function fails, we guarantee that we've deallocated the resource in Rust, so we return true. In previous versions of .NET, there used to be a whole lot of other fluffing around that you would have to do with handles, like around constrained execution regions and unmanaged code security. Those things don't exist in .NET Core, so this is pretty much what we need to do. We don't guarantee that our handle will be reclaimed, but neither does Rust, so that's probably okay. So that's what the C# handles do. They manage ownership. The Rust handles perform the actual allocation and deallocation, and they ensure that accesses requested by C# are free from data races. Because C# doesn't guarantee data race freedom on its own, we have to do that on the Rust side. So the way that we do that in Rust is by using two traits. And those traits are send and sync. They both model part of Rust's concurrency story that makes sure at compile time that data is only used in ways that are valid. If you've written Rust before, you might have encountered send and sync, but you might have only encountered them because you didn't satisfy them and got some weird compiler error that didn't make a lot of sense. Send and sync are what are called auto traits. Auto traits in Rust are automatically implemented for you based on the contents of your type. So you don't need to manually implement these unless you're doing something kind of weird, which is exactly what we're doing. So intuitively, send and sync work like this. So send tells us whether or not it's safe to transfer ownership of some value to another thread. So on the left-hand side, we create some state and we move ownership into another thread from that move keyword. That requires send. Some types that aren't send include unsynchronized ref counts like RC, or types that use thread local state that's not actually going to make sense on the other thread. Sync, on the other hand, tells us whether or not it's safe to concurrently access a value. So on the right-hand side, we don't move ownership into the thread, we send a reference and we try and use it. Because both threads may be accessing that value at the same time, we require sync. So some types that don't implement sync by default are types that have unsynchronized interior mutability, which we're going to have a look at. So we can think of send and sync. They seem kind of weird at the moment, but we can think of them as modeling Rust's concurrency story as relationships between its fundamental reference types. So send and sync tell us something about owned types and references to them. So what sync tells us is that if an underlying value is safe to access concurrently, then a shared reference to that value is safe to send to other threads. And this is kind of the crux of how Rust guarantees data race freedom. Because if we can't send shared references to other threads, then we can't access a value concurrently. And we're going to see that exclusive references behave basically the same as owned values in this case. So we say that an exclusive reference to T is sync if the T itself is sync. You may think that that actually gives us a place to create a data race where we might have a shared reference to an exclusive reference, so we can have shared exclusive references passed around. Rust doesn't work like that. An exclusive reference behind a shared reference becomes immutable, so we don't have a data race there. One of the subtle ones is send. So if an underlying value is send, that doesn't tell us anything about a shared reference because it's not necessarily safe to access concurrently. But we require that an underlying value is send if we want to send an exclusive reference to it to another thread, which may sound kind of weird because we're not actually sending the value, we're sending a reference. But in Rust, it's possible for us to move out of an exclusive reference using something like mem_replace. We can move out of it and replace it with a new value. And that would only be valid to do if the underlying value itself can be sent or moved into the thread that has the reference. So that's what send and sync are all about. If we think about what we need or what contract we're given by .NET, we can figure out what our handles in Rust, what our values in Rust need to do to satisfy data race freedom. So in .NET, we don't guarantee synchronization of values. You can use the lock statement, but you can also just use it incorrectly, which is something we've done in the past. So we need sync. We need to guarantee that whatever C# does, because it will try and access values concurrently, that it's safe for that to be done. Similarly, finalization is an interesting case because even if we manually dispose a value and it doesn't reach finalization, sometimes we might forget and it will, and .NET will run that finalization code on another thread. So it will move out of our unmanaged resource from a different thread than the one that allocated it. And so to do that, we need send. So our handles need send and sync. And that leads us to two different handle designs that achieve these bounds in different ways. So we'll look at handle shared first. It achieves send and sync through interior mutability. So what that means is that it's just a simple pointer. It relies on the underlying value being send and sync. It doesn't add any semantics of its own. This is kind of what it looks like. It looks a bit like ref, but there are some impls here. Because our handle shared is semantically a shared reference, we say that our handle shared is send when a shared reference to the underlying value is send. Similarly for sync. When our handle shared satisfies these bounds, then we can get a shared reference to the underlying value. So that's handle shared. Handle exclusive is a bit different. It achieves send and sync through inherited mutability. It allows us to pull an exclusive reference out of our handle exclusive value without creating data races. So it looks kind of similar to handle shared, but there's a difference. It has this thread bound of thing in it. You might be able to guess what that's about just from the name, but we use it to satisfy send and sync instead of the underlying value. So we say that our handle exclusive is send when a thread bound is send, and our handle exclusive is sync when a thread bound is sync. And when they are, we can get an exclusive reference. So how does that actually work? How are we able to get an exclusive reference out of a handle that might be shared from multiple threads? The answer is through thread bound. So thread bound is this kind of weird type. It allows us to share values without creating data races by binding them to the thread that originally created them. So it's only possible to pull a reference out of our thread bound from a thread that originally allocated it. It does that by using a thread ID. It stores the inner value in an unsafe cell, which in Rust allows us to convert a shared reference to an exclusive reference. Otherwise, it's undefined behavior. And so we say that our thread bound is always sync because we synchronize on the thread ID. If they're not the same, then we don't give you a reference. So we use this in seek because our read and write transactions are naturally synchronous. They're bound to a thread already. We don't want to have to synchronize on them. So the thread bound just gives us a way to guarantee that we're doing the right thing. And if we So because we're fairly confident that we do the right thing in seek, we also just compile a checkout in release builds. And so it just catches us any bug. So in getting a raw, we return a star mute t from an exclusive or from a shared borrow. In Rust, that's important because we need the exclusive borrow of the underlying value to be disjoint from the shared borrow that checks the thread ID. It's a fairly subtle issue, but if they weren't disjoint, then we would have a shared reference that overlaps our exclusive reference, and that's undefined behavior. So that's kind of subtle. Typically, you don't need to build these things, though. You can just use a mutex. So there was one additional subtlety with thread-bound. It gives us sync, but it doesn't give us send because we store the value in line. If our value reaches finalization, we still need for that underlying value to be safe to move into that finalization thread. So some types just aren't like that. They have some thread local state. So in comes deferred cleanup, which is like thread-bound weirdness ++. It's additionally odd. It allows us to drop values that aren't send without creating data races. It looks kind of similar to our thread-bound. It has a thread ID, but it doesn't store the value in line. It allocates it in thread local storage. So we require t is tick static because the underlying value may live for the duration of that thread. So we don't store it in line, so it's always safe to send the deferred cleanup, which is itself a handle to another thread. In order to access the underlying value, we check it in the thread local storage, which is only going to be correct for the thread that it was allocated on. Where deferred cleanup comes into its own is during cleanup. So when we drop one deferred cleanup, if we did it through dispose in C# in the happy path, we're on the correct thread, we simply move out of our thread local storage. If we're on a finalization thread, then we send a message to the original thread saying that it's got some garbage to clean up that it'll come back and deal with later. So we may end up having our values living for a lot longer than they otherwise would have, but projects like CoreRT use a similar strategy like this already. It's better than creating data races and better than leaking data altogether. All right, so just to give you some examples of some handles that we have like a DB store. This is an instance of our database. It's naturally send sync, so we can stick it in a handle shared. We have a DB writer. It is safe to send because it has no thread local state, but it's not safe to access concurrently, so we stick it in a handle exclusive and it's bound to a thread. Then we have something like a reader. It has thread local state, so we can't send it to another thread and we can't access it concurrently, so we need to stick it in an exclusive handle behind a deferred cleanup. So that's a whole lot of code that we've just looked at and a whole lot of concepts. So let me give you an example of, or show you those concepts at work through our sample code base. So we created a document before through our UI. This time we will go and read that document back out and we'll see some of these pieces in action. Okay, so I've issued a request, a GET request. So the first thing that we do is we begin a read transaction in our C# API. Doing that means calling a binding function like we did before. So this is what the bindings look like. We have this maybe check function. And what maybe check does is it calls check on the DB result that we looked at earlier for us. And so we have our DLL import, we have our calling convention. We also specify exact spelling because, you know, that does some stuff for us. So back over on the Rust side, we're in our binding code now. What we're going to do is allocate our reader handle. And so in this case, remember our reader is not safe to finalize on its own. So we allocate it in a deferred cleanup. We're not going to have a look at the new, the implementation of deferred cleanup new because it's really ugly and I don't want you to see it. So we allocate it and we return OK. Now we're going to use some new bits from the .NET Core 3 SDK in order to write our document back into the response stream. So what we do is we start an array. We're going to enumerate all of the documents in our database. That means calling a binding function. So we call our binding function, and now we're back over in Rust. What we do is we get a reference to our reader handle. We then pull a document out and we read it into the C# provide buffer, which in this case is an out. And so if we recall from before, it's okay for us to get a reference to those uninitialized bytes from the out because we're going to read into them without writing, or we're going to write into them without reading. So we've written our document, so we return OK. We then return that we had some data, so the buffer wasn't too small and we're not finished yet. So we materialize some data. So in this case, we have an iMemory owner and we have a range of the data that we wrote. Because data takes ownership of the underlying buffer, we don't just give it a span, we give it the owned memory. We then write it as a value. So that means calling this write the string as a key, or write the key as a string, and write the value as a property. So this is part of the new system text JSON stuff. So now we're going to try and read the next document. So we call our binding function. We get a reference to our reader. There are no documents, we only created one, so we say that we're done. So we end the array, we've finished our for each loop. And now we dispose our read transaction because we're finished with it. So we call another binding function. We complete the reader. And now we're going to drop our deferred cleanup. Because we did the right thing, we're on the right thread, we call dispose. Then we just move out of the inner value. We don't need to create any garbage on the queue. And there's that document that we wrote earlier in the session. Okay, so we've looked at what a hybrid app is, why you might want to write one. We've had a look at Rust, and we've had a look at C# and some features of the .NET runtime. So what might be coming up next for hybrid apps in the future? You might think that something like WASM, as a technology that allows you to take your favorite language in more places, might give you no real need to create hybrid apps. So you can just take C# everywhere. And if that's what floats your boat, then that's awesome. It also gives us an opportunity to create more hybrid apps. We can share components between C# and our JavaScript runtime. Like if you have a query language, for instance, that you want to share an implementation of, you could do that. Similarly, shared compiler platforms like LLVM make it possible for us to stitch languages together more tightly than ever before. So those demos that I was showing you before, where we could step through C# and Rust in a single debug session, were possible because we were using core RT to compile our C# ahead of time, statically linking in our Rust library, and so they're effectively one binary. And so we are debugging then using LLDB rather than the core CLR debugger. So that's pretty well it. I hope you got something out of that. That was a pretty whirlwind tour of Rust. So please come and find me or reach out on Twitter or anywhere if you have any questions. Thank you all very much.